Hello, and welcome back to Daily Dose of Space. Today we're talking about something that sounds simple at first, but becomes surprisingly complicated the deeper you look into it. Humans have walked on the moon. We have astronauts living in orbit. We send probes to the edge of the solar system. And yet, despite all of this, human space exploration seems to stall the moment we try to go truly far. So today's question is not why we want to explore space, but why it's so incredibly difficult for humans to do it. Not because of motivation, not because of technology alone, but because space itself is fundamentally hostile to human life. Space is not empty. From a distance, space looks calm and quiet. In reality, it is one of the most aggressive environments known. There is no air, no pressure, and no natural protection. Temperatures swing violently depending on whether you're exposed to sunlight or shadow. A spacecraft can be heated to extreme levels on one side while freezing on the other at the same time. On Earth, our atmosphere absorbs most harmful radiation. In space, that protection disappears almost instantly. High-energy particles from the sun and from distant supernovae constantly pass through spacecraft walls and human tissue. This radiation damages DNA, increases cancer risk, and affects the nervous system. And unlike many other risks, radiation exposure accumulates. It doesn't reset when a mission ends. The longer humans stay in deep space, the more this damage builds up. Radiation, the silent mission killer. Radiation is one of the main reasons why long-term human missions remain limited. Astronauts aboard the International Space Station are partially protected by Earth's magnetic field. Even so, they receive significantly more radiation than people on the ground. Once you leave Earth's magnetic shield, radiation levels rise dramatically. A mission to Mars would expose astronauts to months of continuous radiation during transit, followed by additional exposure on the planet's surface. Mars has a thin atmosphere and almost no global magnetic field. That means radiation reaches the ground far more easily than on Earth. So far, no spacecraft has provided enough shielding to fully protect humans from this environment without becoming impossibly heavy and expensive to launch. Microgravity and the human body. Gravity is something we rarely think about, but the human body depends on it constantly. In microgravity, muscles weaken because they no longer support body weight. Bones lose density because they're not under stress. Even the heart changes shape because it no longer works against gravity to pump blood upward. Astronauts exercise for hours every day just to slow these effects down. Even then, some damage cannot be fully reversed. Long missions introduce additional problems. Fluids shift upward in the body, increasing pressure inside the skull. This can affect vision permanently. The immune system becomes less effective. Wounds heal more slowly. A mission lasting years, rather than months, pushes these effects into territory we have never fully tested on humans. Life support is a constant balancing act. On Earth, survival is effortless because the environment supports us naturally. In space, survival is artificial. Every breath, every drop of water, and every degree of temperature control depends on machines working continuously. There is no backup environment. If a life support system fails, the margin for error is measured in minutes. On the International Space Station, this risk is managed through redundancy and constant resupply from Earth. Deep space missions would not have that luxury. A Mars crew would need life support systems that recycle air and water almost perfectly for years. Even small failures could escalate quickly. So far, we have never operated a fully closed life support system for humans beyond low Earth orbit for extended periods. Distance changes everything. Distance is not just a matter of travel time. It changes how missions function at a fundamental level. In low Earth orbit, astronauts can communicate with mission control in real time. If something goes wrong, help is immediate. At Mars distances, communication delays can exceed 20 minutes one way. That means emergencies must be handled without guidance from Earth. Crews must diagnose problems, make decisions, and live with the consequences alone. This shift from supported missions to autonomous survival represents a massive psychological and operational challenge. The psychology of isolation. Space exploration is not only a physical challenge, it is a mental one. Long missions mean prolonged isolation, confined spaces, and constant awareness of risk. There is no natural environment, no privacy, and no true separation between work and rest. Studies from Antarctic stations and space simulations show that isolation can affect mood, decision-making, and cognitive performance over time. Small conflicts can grow. Stress accumulates. Sleep patterns change. A deep space mission would push human psychology into conditions never experienced before. Energy and power limits. Every system in space requires energy. Life support, communication, heating, cooling, and propulsion all depend on reliable power. Near Earth, solar panels are effective. Farther out, sunlight weakens rapidly. Nuclear power offers consistency, but comes with safety, political, and technical challenges. Power systems must operate for years without failure, because even short outages could be fatal. Designing energy systems that are both durable and safe enough for long human missions remains a major hurdle. Cost and practicality. Human spaceflight is extremely expensive. Sending people requires heavy shielding, life support infrastructure, and complex redundancy. Every added kilogram increases launch costs dramatically. Robotic missions can achieve many scientific goals at a fraction of the cost. They don't need food, air, or protection from psychological stress. They can operate in environments that would be deadly to humans. This economic reality shapes mission planning more than ambition does. Why robots go where humans can't. The farthest objects ever explored were reached by machines, not people. Robotic probes like Voyager continue to send data decades after launch. They endure radiation, cold, and isolation without biological limits. For now, robots are simply better suited for deep exploration. That doesn't make human exploration impossible. It makes it selective. What could change in the future? Some technologies could reduce these barriers. Artificial gravity habitats may help maintain human health. Better radiation shielding could lower long-term risks. Faster propulsion could shorten travel times. But even optimistic projections suggest that human exploration will remain limited to nearby destinations for a long time. Mars may represent the practical boundary of human spaceflight using known physics. Understanding our real limits. The biggest obstacle to human space exploration is not lack of desire. It is the environment itself. Space does not welcome life. It tolerates it briefly, under carefully controlled conditions. Understanding these limits doesn't diminish exploration. It makes it honest. And it reminds us that every human step beyond Earth is not routine, but extraordinary.